It's a great pleasure to be again in Natal. You selected the chairman. Welcome, the chairman. Yeah, sit down. Okay. I'm going to sit down. No. Okay. Thank you very much for this nice introduction. So it's a great pleasure to be back in Natal, to the institute that was characterized by Esteban as the tropical PI. And just like in a real PI, in this tropical PI, you don't need to excuse yourself for doing foundational research. So I'm going to talk about a relatively recent research direction in our group. This work has been done with Flaminia Giacomini. That's basically the subject of her PhD, and Esteban Castro. They are about to finish soon their PhDs. If I would be squeezed to kind of say in few words what it is about, it's about the question how the world would look like if we were quantum particles, or if we were standing on quantum particles. And now comes the spoiler, so if you don't want to know the answer, you can close your ears. The spoiler is the world will most probably look just like it looks for us. Okay. But the more formal title is the quantum mechanics and the covariance of physical laws in quantum reference frame. And the idea, which builds up on many previous works, which I'm going to mention in short, is if you stand on a quantum particle, you can formally say you are in a quantum reference frame, and then you want to describe world around you, and you want to see whether the physical laws are also invariant when you jump from one such quantum reference frame to another, which will be a kind of extension of what we understand right now as a covariance of physical laws, because we usually then jump from a classical reference frame to another classical reference frame. I'll try to be as slow as possible, so I don't need to come until the end. This is the second time I give this talk, but unfortunately some people you see almost every conference, like Tony Yasin, and so he has this pleasure to hear this for the second time, but some of you also heard maybe a talk by Flaminia. Okay, so what is a reference frame? I will just give a kind of short introduction, then I will let you what is the plan of the talk. So what is a reference frame? So usually in physics we consider them, I would say, kind of abstract entities which are just there to specify the coordinates of events. And since we don't think this is very important, and this is arbitrary, we can choose coordinates as we wish, we think that the physical laws, or the form of these physical laws, should be independent of these coordinates, and therefore there should be the same regardless of the choice of the reference frame. And that's what we call the principle of covariance, and it has been very useful in identifying what are physical laws. And here is an example. I will have an Alice and Bob residing, Alice in her first reference frame, and this is the prime reference frame of Bob. And in general, they may observe a certain object or event. They want to give certain coordinates to that, and the relation between these two reference frames, we usually do it in classical reference frame, is given through the, for example, distance. This is a one-dimensional case, the distance between the origins of the two reference frames, and this distance may change in time, and this is specified with this function x of t. Now, if this object is a quantum object, then we can, for different choices of this function x of t, look at different transformations. The first one will be when this is a constant, and this is just the translation in quantum mechanics, and we know that the translation is generated by the momentum of the particle, and for a certain distance, which is here just a variable, a constant, a scalar. And then we can choose maybe a different transformation where this is a uniform movement of the prime reference frame, in which case the generator is a boost generator. It looks like that. You see p and x are the operators on the Hilbert space of the system, and here is the velocity, which is again just a parameter. Okay, and once we know what are the transformations, we can think also about symmetries. What are the symmetries? Are something which remains the same under the transformations, and a particular thing that we are interested in is dynamics, which is given by Hamiltonian, whether the Hamiltonian preserves its form under certain transformations. That's what we call the symmetry, and here is the Hamiltonian in the prime reference frame, which can be expressed in this way. Here we usually consider a time-independent transformation, so we are very used on this first part, but there is a second part if the transformation is time-dependent, and only if this call combination gives the same dependence on x and p as variables of the function, which is the Hamiltonian. If these two functions are the same, we say then we have the symmetry. Okay, so that means the dynamics will be the same independently of which of the two reference frame we are. Okay, so one example of that will be the Hamiltonian of free particle, for example, under translations and boosts. That's so if you put plug here p square over 2m, you will see that this preserves the form. Now, what I want, this is a first conceptual step out of this framework. Actually, the reference frames are physical systems. I mean, and as such, they, should considered as a physical degrees of freedom. Here is an example. We have a ball. This is a quantum. This is a classical object, and we will say that the ball is 10 meters away from the tree, but the tree itself is a physical system, or even maybe we can say this is 10 times the length of our rod. That's the way how we define the distances, and this is not an abstract thing. This is usually something which we can assign as a reference frame, like a wall or whatever, which is a kind of solid and do not change. And that's why we abstractly think about as a non-real degree of freedom, but in general it is a physical system. But since it's a physical system, it should obey laws, and in particular we are interested in quantum mechanical laws. So what this talk is about is actually the following situation. So I will always consider three types of systems. The C system will be the old reference frame. Then there will be some kind of a system under observation. That will be the B system, a quantum mechanical system. And then there is the third system, when I say system from the point of view of the initial reference frame, which will be a new reference frame. And this new reference frame could be even in certain superposition with respect to the previous reference frame. And then I would like to play around. I would like to look external system from the C point of view, then jump on A and look external system from the A point of view, and so on. And this will be much more elaborated very soon. So several questions we may ask in this framework. For example, can a quantum system be considered as a reference frame at all? And if so, which description would it give of the world? And then we can think about generalization of the notion of covariance of dynamical physical laws, and maybe be able to say something whether the laws of physics really are the same regardless of the choice of a quantum reference frame. So it's a broader class of reference frames that we are now considering. So this is the outline of my talk. I will first say something about kinematics, no dynamics. So this will be really transformation to the quantum reference frame, the notion of the relative state with respect to the chosen reference frame. Then I will move into dynamics and the symmetry and how the Schrödinger equation look like from different such quantum reference frames. And then I will spend some time on examples. Superposition of spatial translations will be one example. The other, superposition of Galilean boosts. And then I will play around with the weak equivalence principle in quantum reference frames. And if time permits, also say something about new stuff for those who have heard this before. And this is a spin in relativistic physics. And then finally, I will conclude. So there are many different works on quantum reference frames and different notions. And when people say I work on quantum reference frames, it's really highly ambiguous. There is a work starting with Aharonov-Sasking and Aharonov-Kaufher on quantum reference frame and super selection rules, how the super selection rules are related to the lack of the reference frame. There is a beautiful review of modern physics on quantum reference frame and quantum information. Usually people consider bound in the reference frame and want to communicate, which brings some certain decoherence or search for decoherence-free subspaces and similar thing. There is also fundamental work by Rovelli about relational quantum mechanics, that only relative states, not absolute states, have meaning in physics at all, so relative to certain reference frames. There is a nice work about changing quantum reference frames, where the relation between the two reference frames is not known in advance. But I want to underline a one specific paper and follow-ups of papers, and I'm happy that the two of the authors of this paper are here. This is Professor Angelo Renato, and here and Paul is here as well. And this is something which highly influenced at least myself to start even to think about that. There is a series of papers then by Professor Angelo and his co-workers, different papers along some of covering some of the topics that I put in the outlook. Nevertheless, many of these papers also are different, and also our differs also from the last one in this row. Mostly, and I will by the fact that we do not start from some external reference frame and then going into particular quantum reference frames. So from the scratch, it's a relative state description. But also our focus is a little bit different. We are really interested in covariance of physical laws under this quantum reference frame, and we stick very firmly into Hamiltonian dynamics, which was at least questioned in one of papers. Nevertheless, it's really a beautiful paper, and I will actually suggest everybody to read this. Okay, so here's the setup that we have. I already mentioned there are three systems. So I will call an old reference frame. This will be always C. You can think about that we are sitting in such a reference frame. Then there is a quantum mechanical system B. And there is a new quantum reference frame, which will be denoted by A. And always the description will be given in relative quantities, relative to the reference frames we are sitting at. So, and this description will be always description of the external systems. You never describe yourself and your reference frame. You can think about that your reference frame is actually not a degree of freedom, because you're standing on here, for example, and it doesn't move, and you are actually in the origin of that. So there is no dynamics here. It's not a dynamical reference frame. So what you describes are systems external to the reference frame. So from the C point of view, these are A and B. But once we jump on A, this will be B and C. So you don't. So when you jump from the quantum one reference frame to another reference frame, you also change your systems. It's not only changing a perspective of one system, which was in the case of classical reference frames, you also change what are the systems. Okay, so once clarify this, one may think that the best way is something which we know from the textbooks to use to describe these situations, namely to take both relative coordinates and relative momenta. Okay, so for example, you can think about that you sit on particle 0, if you have n particles, which is a generalization of this case, and then say, okay, the relative distance to particle 0 are these, and then I also use a relative momenta with respect to the particle 0, where there is a reduced mass. And then you can think this is maybe the way how you should always describe when you sit on particle 0, the other particles, but it turns out that this is not canonical. So if you, and this has nothing to do with quantum theory, it's just Poisson brackets, it's not canonical. So it's no guarantees that you will have a Hamiltonian formalism. I think this is a very interesting thing, and one can actually go along this road. But somebody mentioned in the previous talk, there is a dark, what was wood, like that, and it's probably, it's very hard to get anything, get a result out of this. And I don't know how to go along this road. So what we will do is not do that, but stick to the canonicity. And how we will do this? So we will always choose a relative quantity. For example, we can choose the relative distance we are interested in, and then we will complete this canonically. So the momenta we will get through canonical transformation. And that way, we keep then having Hamiltonian dynamics. Okay? So let's give you an example of what we are doing. And it's a superposition of spatial translations. So if we are sitting on a particle C, then we describe B and A, and this is the distance from C, xa and xp. If we are sitting on A, these are QC and QB. And it's very easy, just inspecting this figure, to find out that the QC will have the opposite position of minus xa, and QB will be just the difference between xp and xa. Okay, now there is two possible ways to complete something to be canonically. You can take Lagrange formalism, you think about this as a point transformation, and then you get your momenta. Or maybe you choose some momenta, and if you choose them to be, in a certain sense, the simplest one, namely to be linear in P and not mix X and P, you will find this solution. Okay? And then if you check the commutation relations, you will see that this is still canonical. So everything QB and PB and so on. Okay, so now this is maybe a formal approach to this. And now I give you what this transformation actually, how it acts on a wave function. And I hope that you will find this interesting and will give some justification for this path. Okay, so here are two quantum systems. As I said, this is a B system and this is a reference frame. Now imagine just for a moment that here you both have a well-defined position of B and a well-defined position of A. So this is really the sharp value in positions. Then we know how we translate from the C reference frame into the A reference frame. So this is a C reference frame in which I see A and B. But I want now to jump into the A reference frame. So it's easy to do, as we said. You need just a generator of translations acting on a B particle, and alpha is just the distance between the two reference frames. And then you will move the position of the B particle. Now what this transformation does is actually a kind of linear extension of what I said. What you do here, once you have a non-local wave packet, if you want, of wave function, then what you do, you integrate over all alphas, and then each this amplitude is a weight in this integration, and for each alpha you move particle B for the distance where you are. So if you're at the distance alpha, you will move just as above the particle B for this. This is a generator. But then you have to integrate. Wherever you are, weighted by the amplitude of a particle, you shift the particle B. But once you rewrite this in terms of not of position representation, but you write this as operators, you see that what you have here is a kind of a extension, quantizing the usual translation transformation. And the only difference between these two is that now what was a parameter before now becomes an operator in the Hilbert space of A. And this is nothing else than wherever A is, you shift B for the distance between initial reference frame and this position where you are. So in a sense, this is not anymore a parameter, but an operator and acting on two Hilbert spaces. Okay, so this is not the full transformation. This is just that if I sit on A, how I see B. But I introduced before that once you jump into the A, the systems that are now external are not only B, but also C. So we need also C to reappear in the whole thing. And here is what we propose, to use a parity operator and a swap between A and C. So whatever the state was of A before, it will transform into, so psi of x will transform into psi of minus x, just to reflect this thing. And therefore, this is a full transformation. So on one hand, we transform B, as I explained here, and then we just need to swap what was the state of C, it will become A, and the other way around. And that's the operation that we now want to continuously to apply. I will come up with few new examples, just to try to convince you that this may be a proper way to deal with this. So whenever we have a state of A and B as seen from C, we will apply this operation and transform into the state of B as C as seen from A. Now, there is certainly a kind of a problem with this because we don't have an experimental evidence for that. We cannot sit on a quantum particle. But then later on, I will tell you something which we can do, which gives maybe some justification that this operation is actually correct. So here are the examples of relative quantum states. So imagine now, first from the C point of view, that A is very, very well localized and B is delocalized somewhat. Now, if you jump in, what this transformation does is if you jump onto the A, so now A becomes a reference frame, then C will acquire exactly the quantum state of A, but it will be from the left-hand side, not on the right. This is this swap operator. And B will be a little bit more extended for extension of the A system. Now imagine now a different situation in which A is a product state, but is in a special superposition of two localized amplitudes. Now if you jump into the A, what will become delocalized is actually C and also B. So what you will get that if I'm here at this position, then I will have this C and this B. If I'm on the right-hand side, that this A and this B. So you will get actually entanglement. Depending whether I'm here or here, I will have a different product states for C and B, and in some, it will be entangled state. So something what was a product state will become entangled from by changing the reference frame. Here is the opposite situation. Here I start with the entangled state between A and B, such that the distance between A and B is the same. Now, if you jump into the A, what will happen is that B will be factorized out because it's always the same distance from A, and C will become a superposition of two localized states and a continuous version of what I just said is an EPR state in which you have a continuity of A and B's, which are on the same distance. And again, the B will be factorized out and C will be totally delocalized. Okay, now I want to move into dynamics of quantum reference frame. And now I will not talk only about the states, but I will also assign Hamiltonian to the systems, all external to the chosen quantum reference frame. And as we start from the old quantum reference frame, I will have a Schrödinger equations. This superscript is where I am, in which reference frame, and A and B refer to the system that I describe. So I start with some Schrödinger equation, and then since I apply this transformation, I can easily then find out how that I can still have a Schrödinger equation in A reference frame. If my new Hamiltonian has this form, again, this is because the transformation could in general be time dependent, and we will introduce in next slides one such transformation, and this is, of course, how the state should transform under this transformation. Now we can also define the symmetry. But now it's a little bit tricky how to define the symmetry, because in the previous case, when I was jumping from one classical reference frame to another, the system was always one system. This was system B. Here, I also changed the quantum system. So when I was at C, I was talking about A and B. When I'm at A, then B, C. So a possible way, so you change the system, what I want to say. A possible way to define the symmetry is the following, that you have a Hamiltonian in the original reference frame, and it has certain functional dependence on momenta, position, and masses of particles A and B. And the symmetry transformation, the transformation is symmetry when the transformed Hamiltonian keeps the same functional form. But now it's, of course, masses and position momenta of the different system of B and C. So if this is the case, we will call this symmetry. Of course, in the special case, when you get rid of C and A, it has the usual form that we are used on. This is a possible extension. Okay, good. Once having this, I want to tell you a little bit about how to work with this in general. Not about only translations, but in general transformations. And this is a little bit more involved slide, but I will try to be slow. So you always start from some classical reference frame, or abstract reference frame, I call it here. And transformation, when you change from one classical reference frame to another, could in general be a product of exponentials. This is because sometimes you have more generators of this transformation. So far, we consider only when we have one exponential. And usually, we have some generator of transformation on the particle B that we want to, the view on this particle B we want to change. And then we have some function or parameter or time-dependent function, which describes the relation between the old and new reference frame. And it was, in the previous case, really a time-dependent function x. Now, what we do when we quantize this is, first of all, okay, so it's a little bit longer, as you see, yeah? But now I want to describe each individual part. First of all, let's look at this exponential part, which is the analog of this. Only what we change here is that we put here a hat, and this becomes a time-dependent operator acting on a Hilbert space of A. But then we have also some other things here. For example, since this is a time-dependent operator, it's given in a Heisenberg picture. But we usually have these transformations acting on the states in the Schrödinger picture. So in order to map to the Heisenberg picture, when we can apply this in a Heisenberg picture, we need to change to the Heisenberg picture. So we map A to the Heisenberg picture, because this is in the Heisenberg picture. And this we do with Hamiltonian of the new reference frame as seen from the old one, from the C. Okay, then we perform this operation. Then we have this parity operator, which switches the equations of motion of A and C, just like we had it in translations. But then again, we want to map back to the Schrödinger picture, but now only C, because now by changing this, we move to the B and C Hilbert space. And this moves C back to the Schrödinger picture. So that's a long kind of expression. But it's an expression that actually quantizes the above change of the classical reference frames. Okay, so, and this, of course, is a Hamiltonian of the old reference frame is seen from the new A. Okay, so here is an example of this application, of this general form, for something which is also familiar with us. And this is superposition of boosts. This is another second explicit example of the formalism. So what I consider here that we are residing in this reference frame C, and we see another observer on a platform, but this platform is in a superposition of velocities from our point of view. And also there is a quantum system here in the momentum representation, and we would like to know if we are given description from the C point of view, how the C and B will look like when we jump on this platform, or from the Alice point of view. Okay, and here is the expression that I had in previous slide applied to this example. So we have here a free particle evolution, which can be, which is the physical system corresponding to the moving reference frame with a uniform velocity. And again, well, this is a free particle Hamiltonian of A, and this is a free particle Hamiltonian of C. And then in the middle, we have the usual thing, but importantly, this is a boost of a Galilean boost on particle B, but it's conditioned on the velocity of A, and the velocity is now an operator. So again, I have here an operator acting on A and B. And of course, I have this parity swap, which sets the velocity of C to be the opposite of the one of A. So this is a transformation that we suggest to apply when you jump from C to the A. And what happens, and this is kind of interesting, is that this is a symmetry of transformation for the free particles, and that's some kind of extension of what we understand, that the boosts are also symmetry when you jump from classical reference frame to another classical reference frame, and then you consider only B system. And now you have a slightly more involved situation. At the beginning, you have A and B. They were free particle, and it turns out that if you apply this transformation on this Hamiltonian, you will get again free particle. So no matter whether you're in the C or A, the world around you will be a view of the free particles. Okay, so here is an explicit example of how the state changes under this jump from one quantum reference frame to another. So here is the system A in the superpositional velocity, as I said. And this is the state, how we describe from the C point of view. So you have here in example only two momenta of A and some state of B. When you jump to the A, then A for A is not anymore a degree of freedom, but what you describe is external systems, and these are C and B, and they become entangled. Why they become entangled? Because the C will take the opposite velocity of A. These are these two opposite velocities. And the B will be boosted, but the boost will depend on the velocity of C, or the initial velocity of A. So for different velocity, the state of B will be boosted by a different parameter V. And so that's what this transformation does. Okay, so now I want to turn into a kind of a useful example. So far, I was jumping from one reference frame to another. I was drawing here kind of observers, and I was assuming that these observers have measurement devices to actually make tomography of the states external to them, and so on and so on. And then you can say, well, how relevant it is at all, because we haven't seen them around. And now I want to say that actually reference frame are very, jumping from one to another reference frame does not need to be necessarily a concrete change of the reference frame. Very often we go into a reference frame in which calculation comes out to be easier to handle. For example, in the rest frame, you only have internal Hamiltonians. Everything is static, so it's very useful sometimes to go into the rest frame of a particle, do some calculation, and come back. It doesn't mean that you really sit on the particle and come back. It's just in your thoughts you do that. You transform into the rest frame, you perform some calculation, you find out some effect, and then you come back to your laboratory viewpoint. And that's exactly what I want to do. What does it mean to jump in the rest frame of a quantum particle? Well, in certain cases, we know what to do. So here is an example where you, for example, have an atom moving with a well-defined momentum in the lab frame. And the concrete example that I want now to consider is how should I prepare a photon, or frequency of the photon, such that the photon and atom get in resonance. And we know what to do. I mean, we just need to jump on the atom, in which case it is in a rest frame. And we know that if we jump to the atom, we know what the frequency should be. It should correspond to the gap between two atom levels. But if the atom is moving with certain velocity with respect to the laboratory frame, then I would have something which is a Doppler shift. And if I know what the Doppler shift, so then I will adapt the frequency of the photon to the velocity of the atom, and I will have again a perfect match and perfect absorption. Okay, now the question is, what about if the atom is not in a well-defined momentum? So what does it even mean to jump in a rest frame of a particle that is in a superposition of momenta? And that's what actually our transformation quantum reference frames allow us. So here we some, especially I guess experimentalists, can already feel what the answer should be. But imagine that we don't know that, and only what we know that if we sit in the rest frame, the same is true, namely that the frequency should match the gap. And here, say, okay, I know what the solution is in the rest frame, so I start kind of inverse engineering as what I proposed so far. Namely, I say that I have a photon, one photon with this frequency, and I have an atom which internal degrees of freedom are here described by A tilde. Atom is in a ground state. And I assume that this W, this frequency, is exactly equal to the gap between the first excited state and the ground state. But from the point of view of an atom, I have to introduce another system, and this is the laboratory reference frame, or the laboratory itself. And this laboratory is now in certain state, which is, as you see here written, is not well defined in momenta. It has an opposite velocity of the A when I sit on the laboratory, but when I sit on the atom, then it's laboratory which is not well defined momentum, and this is exactly what is here written and how it evolves in time. And I have a Hamiltonian, which is a Hamiltonian of a free evolution of laboratory, free photon, and an atom. Okay, now since I know that this should be the answer in the rest frame, now I can answer what the state should look like in the laboratory, what I am interested in, because I'm sitting in the laboratory. And when I do this jump to the laboratory reference frame, something interesting happens, namely, first of all, this Hamiltonian gets an interaction term between an atom and a photon, and the state that was the best state in terms of absorption of the photon becomes this state. And this state is, interestingly, what is in a tangled state between the atom and the photon. And whenever atom has some momentum PA, then I have to Doppler shift correspondingly the frequency of the photon in order to have a match between the two. And this is integral over all possible momenta, so I have some kind of a conditional Doppler shift. And it's a highly entangled state, and if you think about that, it should be the answer. And so this is kind of an example that gives us some confidence that maybe what we are doing actually makes sense, and maybe even a way to test this in laboratory. Okay. So now I will go to a weak equivalence principle, and its extension again to the quantum reference frame. So the whole program is take whatever you know from the classical reference frame and quantize this. And here is what we know from the weak equivalence principle. That's something which also in Angel's paper was treated in somewhat different way. So I here read what I mean with the weak equivalence principle. The physical facts as seen from a reference frame moving with constant and uniform acceleration are indistinguishable from those as seen in a uniform gravitational field. And why we say this is, again, I'm coming back to the classical reference frames. I have Alice and Bob. And now the relative distance between the origins of two reference frames is given with a time-dependent function, but this time-dependent function corresponds to the uniform acceleration A. Okay? And what this means is that if I start with a particle, for example, that is a free particle in an unprimed Alice reference frame, by changing the reference frame, I will get a new Schrödinger equation, which is for a new wave function, where suddenly I have a new term, And this new term is actually equivalent as if I would have a uniform gravitational field, where now A takes the role of the gravitational acceleration. And the state that sets this new Schrödinger equation with this interaction term or potential term is the one that can be obtained through, I call here Greenberger operator, because that's where I learned about that from this paper. So it's a kind of an example of a transformation where you have a product of exponentials, as I had in the most general case when I introduced this. So here are some velocities and square of velocities and position of the reference frame. Okay, now all what I want to do is actually to say that this is true, the weak equivalence principle true, is also in a quantum reference frames. So here are the words that I insert are in red now, and so I can read this. The physical effects are seen from a reference frame moving in a superposition of a constant and uniform accelerations are indistinguishable from those as seen in a superposition of a uniform gravitational fields. And here is, of course, so how we will create a superposition of acceleration. Here's an example. So what we see here is I'm sitting on the C and I describe A and B. A particle is in potential and B is what I want to observe. This is our quantum system. And A is to be a reference frame. Now imagine that you have this potential which is piecewise linear potential. Okay? Why piecewise linear? Because then if I create a superposition of two positions for the A particle, then they will be in a different linear potentials, and therefore they will get a different acceleration if you define the acceleration as derivative of the potential. So if you evaluate this operator for the state that is very much localized in this area, then this state will move with this acceleration, or have this operator evaluated like A1, and the other one is A2. So you can create a superposition of acceleration by putting a particle in different areas or regions of this piecewise linear potential. So that's a way how we can actually create these superpositions. Okay, and then the operation that allows you to jump from C to A, it looks like that. There is always this kind of moving to the Heisenberg and Schrödinger picture. But here it's the known part. This is, well, Greenberger operator. But now it will be a generalization of it, because that was what was just velocity or a distance between quantum reference frames become now an operator again. And of course you have this, parity, kind of swap parity operator between A and C. Okay. Now I didn't write this generalization of Greenberg operator because it's just, you don't see any physics out of that. It's a complicated expression, but it's easily to find out what it is. And now, what is the result for a specific states? So this was our initial Hamiltonian, and let's take that we really create this superposition of two states that experience two different acceleration for A. So this is a situation from the C point of view. Now, if we are at A point of at A, so we are here, then what we will see, first of all, that the Hamiltonian initial will change. First of all, the C will now experience as it is in a certain potential. This is usual because we just swap what experience A into the C. But what is interesting that the B will experience also some potential. And this is a potential which is linear in the position of B, as seen from A. And previously, in the classical case, we had here A, we had some just parameter. But now this is not anymore a parameter. This is actually an operator, and depends on position of C. And depending on the position of C, B will experience different accelerations. So you can say that you have some kind of a superposition, if you want, of the gravitational field here. Not a well-defined gravitational field, because you have an operator that corresponds to the acceleration. And the state that was initially like that will transform again in an entangled state, where C will experience different acceleration, and then the B will be changed by the Greenberg operator conditional on what acceleration C is experiencing. So in a sense, the story repeats again and again. But the message is that you can actually extend the set of transformations and symmetries that you know from the classical reference frame into the quantum reference frames. And it seems that laws are robust under this. You can define the covariance under these new transformations. Okay, so now a sentence maybe about the measurements in quantum reference frames. Our initial idea was that probabilities are something which is invariant. So because these are data that we collect, so if we perform some measurements and collect data and collect probabilities, they should be invariant under the change of the reference frames. So you can think about some kind of a generalization of the Wigner's theorem, in which you also have this assumption and obtain that transformation should be unitaries or anti-unitaries, but if you want to then be connected continuously with identities, unitaries. And now you can write these probabilities in a Born rule in both reference frames. You have to change both your measurement operators and the states into those of A. And since you use this unitary transformation, you will see that probability will be the same. The real measurement procedure is somewhat more complicated when you go from C to A, and I must say that I don't get a lot of message out of that, but nevertheless I will let you know what we do here. So you have the initial state, and you want to perform the measurement on by taking an ancilla. So you are sitting on C, you have an ancilla, and you measure a general state on A and B. So you get some kind of entanglement operation of channel here between ancilla and A and B, and then you measure the ancilla. This is the usual measurement procedure as we know in our reference frames. Now if you jump into the A reference frame, the similarly happens, but with important difference that already the B, C, and A are entangled at the beginning. So you have some kind of entangling operation, but they are already in general entangled. And what you measure here, when you transform this from C to A point of view, is a measurement that is performed on C and A together. As I said, I see this more as a formal calculation. I don't have a very nice physical intuition of this part. Okay, so now I will switch into something which is kind of a new, also for people that have heard that, and it's moving towards a relativistic part. And it will be very simple. And it addresses actually a very important question that we are familiar with in quantum information. And this is a spin in special relativity. I guess, I mean, some of you are familiar with this seminal work by Perez, Scudo, and Terno, where they claim that the spin is not relativistic invariant. And the reason for that is that there is by relativistic speeds, actually the spin gets entangled with momentum, and therefore if you trace out the momentum, you have less information. There was a puzzle at the beginning. Now it's kind of, we understand what's going on, but this was a long discussion when I remember. And actually, the problem of the spin in special relativity is a long-standing problem because from the quantum field point of view, the decomposition of the total angular momentum into the angular momentum and the spin is not unique, and there is a huge debate about that. There are hundreds of papers, well, some of them very old. I just show you some of them of the newest. Chakor had his special relativistic spin operator. There is Vlatko Vedral claiming that Wigner rotations are not linear transformations. That was recently. Maybe this is the best way to describe the whole debate. What is the relativistic spin operator? There is also old papers. There is, well, some of them are very old, like in 26. Some of the newest, this is the one that I mentioned, quantum entropy of special relativity. two roles of relativistic spin operators, Daniel Turner, and many more. Okay? And now, maybe one can pick up what is the heart of the whole problem. And there is a desiderata formulated by Bauket and co-authors that a covariant spin operator should satisfy something which we know for the spin in our rest frame, so to say. It should be the have the SU2 symmetry, should have eigenvalues plus and minus h bar half, and has the correct non-relativistic limit. And it turns out that this is somehow problematic, because most of the proposed operators do not satisfy some of those, do not satisfy all of them. They can satisfy some of them, but not all. And of course, we have no experimental guidance to answer this question. Okay, and now we are actually interested in that, because imagine that you really prepare your spin Stern-Gerlach magnet in our laboratory reference frame, and then we move in some reference frame with a relativistic speed, and we want to know where the quantum information is stored. We still want to be able to operate with this, transform, measure, and so on. And now we don't know where it is, in a sense. And so there is a solution with these tools, what I want to say. It's a solution with quantum reference frame. And the solution is the following. We know operationally what the spin means in the rest frame, because we know how to perform the Stern-Gerlach experiment. We know what spin algebra, Pauli operators, and so on. So the idea is, well, wherever there is a particle with a relativistic speed and a superposition of relativistic speeds, move to the rest frame, define their spin observables, just like we used to do that, and go back to the laboratory frame. Okay. Now, if the particle moves with a well-defined velocity, this is the usual Lorentz boost. And what it means is that, well, if you have a rest frame, and this is a 4-vector, both are 4 vectors, you have a spin, degree of freedom, and the momentum. Now, if this is in the rest frame, and then you move in some relativistic frame, then your state of momentum and spin will change by some relativistic boost, and will change in such a way that not only you will get some momentum of your particle, but also your spin will rotate, and this rotation, this is important, will be dependent of the momentum. But if this is a well-defined velocity, we know how to do it. It's exactly like that, and we know where the spin is. Here is the spin. I mean, this is the direction of the spin, and the momentum is fixed. Okay, but what happens if we don't have a well-defined, if I don't have a well-defined momenta, but the particle is in a superposition of relativistic momenta, how should I jump onto the particle? That's exactly the same question now in the relativistic framework. Okay, and here's the solution. And the solution is, again, well, I don't know how to do it, but I know what the solution will be in the rest frame. So I assume that in the rest frame, I'm sitting on the particle, and what I can see is the spin of the particle. That's spin of the particle in the rest frame. And what I see is laboratory. But since the particle is in a superposition of momenta, if I'm sitting on a particle, laboratory should be in the superposition of momenta. So I assign a state to the spin and a laboratory, where the laboratory is in a superposition of momenta. Okay, and then I know what the spin is. I know how to measure it. I know how to transform it, and so on. And then I want to go back. And I will do this with a Lorentz boost. And what it means is the usual thing as we had so far. This is the Lorentz boost from the previous slide. This is the same Lorentz boost from the previous slide. But now here it becomes an operator. It will depend on velocity of the C. And at the end, I have to swap what C and A are quantum states. So I have a Lorentz boost by each velocity of the laboratory relative to the particle. And if I do that, then I have in the laboratory frame something which looks is entangled, because I will have a different momenta of A, and for each different momenta, I will have a rotated spin that corresponds to this. And now this is a state seen from the laboratory point of view, state of the momentum degrees of freedom of the particle and the spin degrees of particle. And this actually allows me, with this operation, to define the spin operator. And the spin operator is just take the spin operator in the rest frame and change it with this transformation that I had here before. And if you do that, you will see that you have a correct non-relativistic limit, because when the velocity goes to 0, I don't rotate the spin. The spin is the same. I just have a change between C and A, but the spin doesn't rotate anymore. I have a SU2 algebra, because this is a unitary thing. This I will satisfy. And also I have a correct eigenvalues, because if I have a correct eigenvalues in the rest frame, then I also have correct eigenvalues in the laboratory frame, where here I have now the state in the laboratory frame. So this is a spin, and this is a state of the laboratory. But when I apply this SL, I'm jumping onto the particle. Then I'm jumping back to the laboratory, and this is the state in the laboratory frame, the state of the spin and the momentum degrees of freedom. So in a sense, we achieved what has been asked for. So the way how I understand this is that this total Hilbert space is actually a fiber bundle. So the projection is the Hilbert space of the square integrable functions of momentum, and the fiber is actually the two-dimensional block sphere on the top for each momentum. So this new operator somehow thinks that it goes to every momentum and then identifies what is the spin up and spin down. And for every momentum, it will be a rotation of the spin block vector, but it collects all plus ones in each of these subspaces, and it's a highly degenerative operator. Okay, with this, I would like to come to the summary of the talk. So I think the main idea behind is an operational approach, where we really think about reference frames as physical systems that obey quantum mechanical laws. We have shown certain generalization of the covariance laws and symmetries to these quantum reference frames, and in particular, we look at the superposition of spatial translation and superposition of both Galilean boosts and also relativistic boosts, generalization of the weak equivalence principle to quantum reference frames, and also we found a relativistic spin operator that actually satisfied the spin algebra with correct eigenvalues and correct non-relativistic limit. And with this, I would like to thank you for your attention.